Today's episode is sponsored by Applied Technical Services, your partner in quality, safety, and reliability. Visit them at atslab.com.
Aerospace and defense manufacturing.
Machines and automation.
Additive manufacturing.
Smart manufacturing.
The global manufacturing economy.
Welcome to Advanced Manufacturing Now, the podcast for manufacturing professionals, powered by SME. From the design screen to the shop floor to final assembly, we drive the conversation about making manufacturing smarter by connecting people who are passionate about manufacturing.
Hello, and welcome to Advanced Manufacturing Now, the podcast for manufacturing professionals. If you haven't already, like and subscribe to get new episodes delivered to your inbox each week. I am your host, Lawrence Moebs, editor at SME. Today, I am joined by Jerry Capo and Dr. Alex Kinsey. Jerry Capo is the Vice President of Technology at Product Evaluation Systems located in Latrobe, Pennsylvania. PES, Product Evaluation Systems, is a part of the ATS family of companies, and ATS is, of course, widely known as a leading provider of testing, inspection, and certification solutions across a broad array of industries. And Dr. Kinsey is the technical lead of the Metallurgy and Failure Analysis Group of ATS, based at the headquarters in Marietta, Georgia. So welcome to the show, gentlemen. Our topic today is the importance of testing additively manufactured components. But before we get started, Jerry and Alex, is there any other background information you'd like to share about yourselves or about ATS or its sister company, the Product Evaluation Systems? How about we start with Jerry?
Thanks, Lawrence. No, I just want to say thank you very much. We're appreciative of the opportunity to talk to you today. And ATS and PES are both long-time testing laboratories that service our customers in the best way that we can every single day for mechanical, metallurgical, chemical analysis, and non-destructive testing. So we appreciate this opportunity to meet with you.
All right. And now Dr. Kinsey.
Yeah, no, I'll echo what Jerry says, and just give a quick little background. So ATS does a lot of testing, inspection, certification, calibration, but what Jerry and I really focus on is the testing segment. And so we dive into the standards and the testing of material properties each and every day. So excited to talk about how that pertains to additive manufacturing.
All right. Thank you very much. And as we go through some of the questions I have for you today on the podcast, I'll ask the question and I'll let either one of you can jump in with an answer, and maybe the other one can give some follow-up if they choose to. So we'll start right out with the big question. Why is testing of additively manufactured parts so important?
I guess I'll start off. That really is the most important question. And the explanation is testing and characterization of any and all materials is crucially important so that we can guarantee that components can meet the performance requirements that they're designed for, while also fitting within the constraints of size and cost. And at the end of the day, that's what it's all about for any component, regardless of how it's produced, whether it's additively manufactured or conventionally processed as, say, a casting or forging. In the case of additive manufacturing, forgings, castings, it really doesn't matter. The mechanical properties are what dictate the ability for the product to perform well in service. But the mechanical properties are dependent upon two primary aspects. One is chemistry, and the other one is its underlying microstructure. And so both of those play critical roles in how the mechanical properties are going to be, exemplified in the part, in how it's going to be performed ultimately in service. So testing of AM parts is just as important, if not more so, than conventionally produced parts due to the complexity of the processes involved and how much ability we have to tune those parameters within additive manufacturing to sculpt and create both unique products with unique properties that in some cases can't be produced conventionally. So in a lot of ways, testing of additive manufactured parts is even more crucially important at this stage in the game than, say, conventional parts, because of its ability to be tuned to very discrete levels. So for those reasons, this is why testing is so critical.
Oh, yeah, I was just going to piggyback on that a little bit. One other thing, and I'm sure we'll speak to this more as we discuss, but additive manufacturing is still a relatively new technology. There's still a lot of learning curves that are going along in industry. And so why do we have to test? Well, we have so much variability. There's different types of printers, different processes, and within each individual process, there's even new alloys that are being developed to be used with additive manufacturing. And that doesn't have the benefit of decades and decades of experience and data that we have with conventional raw materials. So in order to validate that the material is performing as desired, well, at the end of the day, you have to test it, whether that's full component testing or individual, material-based testing of, tensile bars, hardness, et cetera, but we have to make sure that it's working as intended. And so that's a real driver for testing both the components and, your build volumes for additive manufacturing.
All right, now, Jerry, you hinted a little bit at this already in your last response, but I want to ask both of you a little bit about the testing requirements, how they're similar and different with additive manufacturing and conventionally manufactured parts. So some of the big differences and the big, testing requirement differences and why that's the case.
Yeah, well, here, I'll take the first crack at this. So at the big high level overview, the testing is the same, right? It's not like for the most part, we're not developing new tests all the time. We're still doing tensile bars, we're still doing fatigue tests, we're still examining microstructure. So those basic tests are equivalent. It's just the number and specificity of where and how should be adapted to the additive process. So take, for instance, a casting, right? Oftentimes to validate material properties in a cast sample, you'll have what's called a ride-along, where you cast a sacrificial bar outside of the mold, and that's what you test to validate your properties. Well, similar sorts of techniques can apply to additive, where you build a tensile specimen or specimens really on your build plate, and that's what you test to validate that, hey, this build performed just as well as when you first did it, or you designed the process to begin with. So in short, most of the test methods are quite similar. It's how many and where with respect to the parts that gets a little different. One thing that I'll also mention is, the emphasis on what kind of testing can change. So, for instance, wrought product, you're often not doing that much, CT scanning or X-ray on those because they're fully dense parts. But with additively manufactured parts, especially powder bed fusion, you have the risk of a lot of porosity, or if you're building internal channels, you have trapped powder. So these non-destructive techniques, I would argue, have some more utility when you're doing additively manufactured components. So those kind of tests might have more value for AM versus some of the conventional subtractive methods. The other thing that I'd hit on is, and this kind of additive manufacturing kind of borrows from a lot of previous techniques. So there's a little bit of casting, there's a little bit of powder metallurgy, and then there's techniques that are pertinent to those manufacturing methods that kind of marry together in AM. So one really important metric there is part density. So there's no part density specific standard that I know of yet for additively manufactured parts, but there is powder metallurgy part density standard. And so that one's typically used, again, to quantify, are you building fully dense parts? Not an issue with raw product, but certainly can be an issue when we're getting into the additively manufactured space.
Yeah, I definitely see the need for that kind of testing. Anything to add to that, Jerry?
I think Alex hit the key points there. One thing I'll mention is he did talk about non-destructive testing, inspection work. In a lot of ways, additive manufacturing processes are akin to a hybridized manufacturing process that's somewhere between conventional, say, casting and or wrought product and welding. And so some of the inspections that are common that we'll perform on weld products are also applicable to AM parts. And so from that standpoint, as Alex mentioned, density and porosity measurements, some of that can be true, yes, in castings, less so maybe in wrought product, but for sure there are considerations that need to be taken account of when you're talking about an AM part. And the last thing that I'll kind of mention is different than, say, castings and wrought product, orientation effects can play a large role in mechanical properties and how those mechanical properties are portrayed by the material, depending on whether you're talking within an XY plane or in what we call the Z plane or Z axis, which is the vertical portion of a build. So it's the buildup of all the layers, and some properties really are irrespective of those layers, and some properties are highly dependent upon how the material behaves as the stress is applied across those layers. So orientation effects can play a pretty large role in AM produced parts, and therefore some of that testing becomes more specific and sometimes more involved in AM produced parts than, say, a casting or a forged product.
Yeah, that makes a lot of sense for sure. Alex, you mentioned about the kind of the newness of the technology. That's one reason for the testing, being so necessary. But to a lot of individuals and groups, additively manufactured properties and parts seem to be a lot more scrutinized than conventional manufactured parts. Is the extensive extra testing that's going along with AM parts, is that just because of the newness, or are there other things going on, especially if the material and part geometries are the same?
Yeah, I'll let Jerry talk to this one.
Yeah, no problem. So yeah, your point, and both your points, Alex and Lawrence, are valid. So when you take a look at castings, for example, people have been casting products in one way or another for, it's arguable depending on, what historical background you look at, but 6,000 plus years we've been casting products, and we've been forging products for upwards of 9,000 plus years. If you compare that to additively manufactured parts, they've theoretically been around for about 70, 80 years, but in practice, really since the 1980s. So we have about 40 years under our belt. And in the scheme of things, that sounds quite in its infancy if you compare that to, say, conventionally processed materials. And yes, it is. However, we have all of that history that we can build upon with conventionally produced products. And we also have the ability to now study materials at a much faster rate, understand the impacts of process changes on underlying microstructures, and we can take advantage of design shapes, and printing practices can be tuned to really optimize those in a way that may have taken hundreds or thousands of years to optimize before. We could do that much quicker now with AM, but it is something that has to be acknowledged. It doesn't have the history that we have. Yes, we can learn and take advantage of what we know concerning conventionally processed materials, but we still have some catching up to do on exactly how, when we turn particular knobs within an AM process, what impact that has ultimately on the parts microstructure, even chemistry to some aspects, and then how that influences the mechanical properties and how it'll perform in service. So, um, the other thing is we have literally thousands of process and product specifications and guidelines today for conventionally processed materials. And if you follow those correctly, we could produce a part that's pretty repeatable, very reliable, high quality. So far, the technology associated with AM really kind of outpaced the specification creation, and we're playing a little bit of catch up as an industry. And there are a number of specifications out there now, and we can talk about those later. But as far as those specifications are concerned, we're trying to play a little bit of catch up there. So, in terms of how one person does it versus another, that can vary greatly depending on the process they use, the equipment they use, how they particularly set up those parameters and builds can be quite different. So the capital investment that's required for 3D printing of metals is far less in many cases than, say, the capital investments that are required to start up a casting foundry or a forge house. And so a company could literally buy a printer and start making parts today much faster than they could if they were trying to set up a conventional cast house, let's say. But will they produce high quality parts right off the bat? Do they understand the nuances of the parameters and the settings associated with those builds and their feedstock? These are things that, we have progressed slowly over time for castings and forgings, and over hundreds or thousands of years, this knowledge has been built up and transferred from individual to individual, industry to industry, and we've been able to take advantage of that and build upon that. The ability to produce in 3D printed materials in the equipment that build the equipment that make those parts has progressed so rapidly, relatively speaking, that in some ways it's outpaced the knowledge of how we should produce them. And so that's something we have to be aware of. That's something as an industry that we are aware of, but it's nonetheless, it does kind of, highlight the importance of testing that we talked about earlier. So there are a lot of AM processes that use different feed sources as well. So whether you're talking a powder, a wire, solid state fusion process technique, all of these things go into this inherent variability associated with AM. That doesn't mean it's bad. It just means we need to understand it, and we need to understand how those changes affect microstructure and ultimate mechanical properties. So,
yeah, definitely. It's definitely, like you mentioned, definitely a new industry, a new technology, but there are some specifications that are, being put in place. So what can you tell me or tell us about the specifications and regulating bodies overseeing and prescribing the testing requirements? Where are the requirements coming from, and who are the regulating bodies involved?
Yeah, so at the end of the day, this comes down to, where the part's going. So a lot of standard organizations, ASTM, ADBS, NASA, have started to put out and are continuing to put out various standards to lay some frameworks for additive manufacturing. There's also certainly a lot of companies that have developed their own internal standards. So like Jerry said, the technology kind of got ahead of the standardizing committees. So people have necessarily put on their own guardrails for testing and certification. And so that's where we see the state of the field at the moment. But hopefully, as the technology progresses, the machines get more standardized, we'll start seeing some more standardization and agreement in the industry at large as to what's really necessary. But I think one thing to think about, especially because I know a lot of manufacturers are listening to this podcast, is it comes down to part criticality, right? And the design authority that's dictates levels of testing and what specifications are required. So if it's a very critical part, by necessity, you'll have to do a lot more testing than if it's just a little widget that's not going to be, a safety related component. And so that helps dictate, one, what standards to use, and then two, the levels of testing. But at the end of the day, it's the design authority, the person that's making the drawing for the component. It's their responsibility to understand the amount of testing required to validate the properties. Otherwise, you run the risk of the part not performing as you intend.
And you mentioned that, it's definitely different, by product to product, industry to industry. But are there some broad categories of testing that producers of additively manufactured components should be looking at just broadly? And are there some critical tests that should be performed right off the bat, kind of across the board?
Yeah, I'll take this one. So clearly we want to perform NDT inspection work, non-destructive inspection work, mechanical testing, metallurgical analysis, chemical analysis, dimensional measurements. We need to understand what the orientation effects are, like we talked about a little bit ago, within the build itself. We need to understand and characterize the feedstock, whether it's wire or powder, and what those characteristics, the size distribution, the shape of the particles, if we're talking powder, chemistry, so on. And then in some cases, we care very much about the surface roughness. In AM, sometimes we're machining the part. At the end of the day, it gets machined and it's utilized like that in service. And in some cases, we want to take advantage actually of an as printed surface and some of the benefits that can come from that, whether it's cost or performance based. And so from that standpoint, these are the types of tests. Again, they're not very different from what we would do for a conventionally processed material, but eventually we need to add statistical assessments of reliability, repeatability into that mix because of the way we produce AM parts and because of the different machines that are used, the different setups that are used, and the different parameters that are implemented. In 2018, PES submitted a Tech Connect proposal to work with NASA Glenn AM engineers to develop a set of testing / characterization guidelines that we could use to propose to our customers if they themselves did not already have internal guidelines or scope of work that they wanted to reference or could reference. And so if a customer has their own set of instructions and guidelines and requirements, great. If not, then we have a set of guidelines that we can propose. And we were awarded the opportunity. We worked in NASA. We ended up developing a series of 3 test matrices based on what we call technology readiness levels, TRLs, with the goal of just saying, okay, if I'm a low TRL level, meaning I'm pretty early in my process, I'm at the initial stages of AM development in terms of either equipment, settings, I'm making rough product shapes, not final components yet. Here are the tests we need to do. And they may be a small portion of mechanical testing, definitely some metallurgical analysis, chemical analysis, so on. Some inspection work for sure. But then as you progress in your maturity and you start making your way towards prototype parts, there are a new set of matrix testing that we would perform. And it's everything within the earlier matrix, but then there's additional testing. And this is where things like fatigue and crack growth start getting implemented, and larger quantities at different conditions, whether it's stress and or temperature conditions, start being applied, so that you can round out your characterization curves that designers will ultimately end up using in the design of the components. And then lastly is a production part / quality control portion of the maturity scale. And that's once you have parts in service and you're just trying to make sure that each set that you make from then on out is produced in the same way as you did back when you were developing your characterization and R&D curves. So the largest test matrix is in the middle portion of that maturity scale that we talk about. And they are similar to how we would build characterization programs for cast and or forged products. But there are some differences, and there's differences we highlighted earlier. But yes, so that's the type of categories we'd explore, and that's the type of approach we would take for something like this, whether we're implementing this type of test matrix, or I shouldn't say implementing, but recommending it to our customers, or they come with their own set of recommendations and guidelines that they want us to follow. That's completely up to the customer. But at the end of the day, we produce the data and the curves that they need for their parts. And that is going to largely depend on material complexity, part criticality, and material selection.
For sure. And I'd imagine the shape and size of different parts is going to affect, how easily they are tested. Can you tell us a little bit about the shapes and sizes that are maybe more or less amenable to testing, and how do they overcome that?
Sure. Well, so this depends on the end use. There's certainly some economic considerations as well. But broadly speaking, in materials, you have different scales of testing. You got the small micro scale or even the nano scale, and all the way up to the big bulk inch, foot, meter length scales. And all those can be tested. But you get different answers, and you're probing different things at those different length scales. So in the general manufacturing and commercial testing spaces that we're in, we're typically testing bulk properties, and that comes from testing tensile specimens, fatigue specimens. You're looking at materials that are inches in length, and that really gives you a good sense of the bulk properties that you have. Now, of course, there are techniques for looking at smaller scale. You can go to micro Vickers testing, nano indentation, small scale tensile testing, but those are really kind of more specialty types of tests that really probe the material properties on the small scale and may not necessarily be representative of the entire material build. But one thing that is important to recognize is those length scales can be important to properties. So just because you get certain mechanical properties when you build a big bulk specimen, that might not translate if you're making a small, thin-walled membrane, a fin or something, or some sort of protrusion. Those mechanical properties may be different. So we can do various small scale, kind of more R&D type tests to prove feasibility of mechanical properties at that small scale, but it might not be translated.
I know that in manufacturing, there's a lot of talk about the waste of overproduction, not just producing too much, but kind of handling things too much and interacting with your processes too much. How do you know with testing that you're not over testing, that you're not contributing to waste there? How do we know how much testing is enough to have full confidence in the product properties? How do we know when we're done testing?
Yeah, that's a very important question, and it depends on who you ask. Producers will say less. End users will say more. But you're right. How do we know how much testing is enough? At the end of the day, the idea of how much do I need to test really boils down to, if I test one chunk of material, regardless of how I make it, how representative is that piece of material to the broader population? In other words, how many samples or builds or components do the test results from this one test article do they represent? So is one lot of powder, do I need to test every lot of powder, or can I test one and have it represent 10 lots of powder? Or do I have to test every single build plate that we produce in print? Or can I get away with testing X number every so often? Do I have to test each and every time I switch machines? So this is the type of question. And so how do we know that? How do we figure that out? It depends on repeatability and the reliability of the data. So how often, how frequently does that change, and how variable are the results? So if I test article A, how repeatable is it if I move from machine to machine, or I change my powder supply or supplier, and my operator, my equipment, and my procedures? How much variability is associated with just the way I process and set up all of my process parameters and tune the equipment? So that's really going to depend from manufacturing technique to technique and manufacturer to manufacturer. As far as mechanical properties are concerned, fatigue and fracture properties are greatly dependent on defects like lack of fusion, porosity, inclusions, etc., plus the interfaces between those layers that we talked about earlier, from print layer to print layer. So understanding how fatigue curves in a particular AM part compared to a forging, for example, is a large focus right now for producers of especially critical components. So there may be aspects that, okay, we only need to check chemistry every so many parts. We'll need to check mechanical properties maybe a little bit more frequently. And until we gain confidence, we really need to spot check certain critical test types for critical applications to make sure that the part that I'm producing will behave as expected. And the goal is to get to levels similar, testing frequency levels similar to castings and forgings ultimately. It'll take a little bit of time to get there because of the age of in the maturity level of this technology. Sure, we will get there, and I think we will get there relatively quickly, but it will take some time, and people have to understand that these types of curves will change depending on some of these variables. And so it all boils down to the end user and the manufacturer, and that balance of how many parts do I need to check so that I'm comfortable that this set of properties represents my entire production line.
Yeah, and just to piggyback on that, I would say, and when Jerry and I were talking before coming on here, we were kicking back this idea that really, testing at the end of the day, it's a risk reduction activity. It's to make sure you have confidence that your component will perform as designed. So just like with conventional processing, the same types of strategies of extensive first article testing followed by statistical process control afterwards, that same methodology applies in additive manufacturing. It's just the quantities and the types that change, right? In additive manufacturing, your lot is typically defined by your build plate. So what's the requisite amount of testing to certify that build plate? Again, that it all comes back to the design authority and the criticality to make those decisions. Maybe you just need to do a tensile, or maybe just a visual inspection could pass. But for those super critical components, it might be, full CT and destructive sacrificial testing of a component to really ensure proper material properties in the critical regions. But it's really the designer needs to understand those trade-offs and make sure they're testing appropriately to make sure their components behave the way they intend.
All right, well, in our short discussion so far, we've covered a lot of ground. You guys have shared a lot of really great information. But are there things that that your customers or that the world of manufacturing needs to be thinking about and considering about testing and additive manufacturing that we haven't covered yet? What other things need to be out there?
Oh, there's a ton. Jerry and I could talk about this all day. um, yeah, well, I'll say, it's important to take a holistic approach when thinking about AM and designing for AM and testing to validate your components. Like Jerry said, looking at these matrices and these specifications that are out there give a very good roadmaps for what testing should be done at a bare minimum, and then really understanding what you're using your component for can help determine what testing needs to be done. And we can help provide guidance as to what we see out in the field, to give that confidence that the parts will perform as intended.
Yeah, I'll just say, the continued development and expansion of specifications is really critical so that we can continue to move towards a standardized. And it doesn't, and by standardized, I don't necessarily mean that everybody has to do it the same way. It's just that the process that they want to use in particular ends up producing a consistent product in terms of microstructure, chemistry, and ultimately mechanical properties. So those standardized specifications, both process and product specifications, I think as an industry, we need to keep working towards that. And I know there's a lot of effort on that each and every day by a number of different organizations and regulating bodies. And the other thing is, communication between the end user and the manufacturer is happening every single day. It's extremely critical that we really understand the end use requirements and what properties are most critical to your particular design. And that may change as you change the shape or end use of that particular product, the environment that it's in, etc. But those types of requirements and that type of collaboration will dictate what properties are important, what level of testing is required, and what level of assurance is needed, at the end of the day for your particular product. Because, if you're making a component that's going to be in a submarine that may be underwater for 6 months, they may have a different set of criteria than, say, something that is relatively less critical in terms of safety implications and so forth. So.
Right, definitely. Yeah, safety's definitely got to be a key consideration, I'm sure. So you both have shared a lot of great information, but no doubt there's going to be people listening to the podcast today or out there who are going to want some more information. So if our listeners are interested, how do they contact ATS and PES for their testing needs?
Well, for ATS, we can be reached online, atslab.com. There's a full-on contact us link section with phone numbers to get in touch with us, and they'll route your questions to the right person to answer your testing needs.
Yeah, and at PES, our website's www.pes-testing.com, or you can call us at 724-834-8848, and we will put you in contact with the correct person to answer the questions that you have.
All right. Well, thank you again very much. I definitely appreciate the information you shared today. I'm sure our audience does as well. Thank you, Jerry Capo, and thank you, Dr. Alex Kinsey. Thanks for joining us today. As I mentioned, you've shared a lot of great insights, and it's been very informative. I mean, for me personally, and I expect for most of the members of our audience as well. And for our listeners who want to learn more about the latest manufacturing trends and hear more podcasts, you can subscribe to our podcast feed, and of course, you can visit us anytime at advancedmanufacturing.org. Thank you.